So now let's look at the what's called the induced drag. And in order to compute this, we need to go back up and look at our downwash relations here again. So remember that we have V infinity here, and that gets rotated by some induced angle of attack to give an effective angle of attack on this airfoil. And that rotation moves the local lift vector, so it's at an angle to the global lift vector, which the global lift vector is perpendicular to V infinity, and that rotation creates a component of lift that's actually in the same direction as the global drag vector. Okay, so this is what's called induced drag. It comes from our induced angle of attack. It comes from rotating that local lift vector by the induced angle of attack. And so we can now compute this, the amount of induced drag created by this wing once we know the distribution of gamma across the wing from lifting line theory. So let's look at how we would do that. Notice that the induced drag is going to be equal to the local lift vector, times the sine of alpha I. That's the component that is in the direction of the drag. Okay, so let's write that down. So our local induced drag at some location z is equal to the local lift times, now that's a function of z, times the sine of alpha I, which is a function of z. Okay, so that's our local induced drag. Now we're going to use a small angle approximation and say that, sine of alpha I is about equal to alpha I. And and we're also going to say that L is equal to rho V infinity gamma at any location z. So put that in there, gamma of z. And so we can plug both of those in, and what we get is that the induced drag is rho V infinity, or is very close to rho V infinity times gamma of z times alpha I at that z location. Now recall from our development of lifting line theory that the induced angle of attack at any z location can be found by integrating the change in vorticity over the length of the wing, and we use this zeta as the variable of integration here. So at some location z, and that's that z there, we have to integrate across the entire wing using zeta to find the local angle of attack, or the induced angle of attack. Okay, so we can now combine this to get the total drag. The total drag is going to be the total induced drag, is going to be the integral of the induced drag from z equals minus b halves to b halves, the induced drag at any z location, times dz. So and we can rewrite that now from our equation up here above for the induced drag. That's simply rho V infinity times the integral from z equals minus b halves to b halves of gamma of z times alpha I of z dz. And that just comes from using this equation for the induced drag, and then and notice that alpha I is in there. Okay, and now we're going to plug this in for alpha I, and when we do that, what we get is a double integral. I'm going to pull the constants out front, so we have rho over 4 pi times the integral from z equals minus b halves to b halves of gamma of z times the integral from zeta equals minus b halves to b halves of d gamma d zeta that's a zeta, d zeta over z minus zeta dz. Okay, so we have this alpha I term here. We've plugged in this integral, brought these constants out front, and added them to these constants out front. So those are all the constants. And then we have this alpha I integral inside of this other integral where we're going integrating in z across the wing to get the total induced drag. But at any location, it depends on another integral to get the local induced angle of attack. So that's why we've got this nested integral here. So same thing as before, we can also look at an induced drag coefficient on the wing, and that is simply non-dimensionalized the way we do any other force on a wing. It's 1/2 rho v infinity squared s. That's what we use to non-dimensionalize, and where s is the wing area. And so if we plug all of this in, what we get out front is 1 over 2 pi v infinity squared s times this double integral. So the outside integral is from minus b halves to b halves. That's of gamma of z. And then we've got an internal integral where we're integrating from zeta equals minus b halves to b halves of d gamma d zeta times d zeta over z minus zeta dz. Okay, so this is the induced drag coefficient on the wing, and this is the actual induced drag. We'll say that's equal to the induced drag there. Okay, so we've now come up with an equation for the induced drag, and of course what we're missing is simply the gamma of z. This all depends on this gamma of z distribution. Once we have that for any single wing, then we can go through and compute the lift as shown in the previous video or the induced drag using the integrals here.